last lecture of mine. Before starting the content of today, a small correction what a few people, even here in the audience, in the small audience, told me. I made a small mistake last time, and a few of you commented me, so just to correct that. So when we did this algorithm of I'm making just a picture of exploring edges starting at the boundary of the k by k box around L, around 0. Well, then we said initially, okay, the vertex set, okay, will be all vertices that are on this boundary, but the edge set, F0, should not be the empty set, but it should contain all those edges and non-edges on this particular set here. So that should be is the set of all x, y in E such that x, y are in B0. Okay, so in particular, yeah, people write, a few of you told me that you could have otherwise such path like this and such path like this. For example, you would say that 0 is connected, which is not right. So you have to, unless you know already that these edges are there. So you have to know which of those edges are there. And these are explored in the first step. The remainder goes through in exactly the same way. So that's the only change that the initial situation, the initial setup of the algorithm has to be such that you check indeed all edges on the boundary, because otherwise those edges will never be checked, because the condition was that you check an edge if there's one vertex in the current set and the other outside. But that would mean that those edges that go between vertices on the boundary will never be checked, and that was a mistake. So that's the correction from last time. Okay. So, a bit of recap. What did we do so far, apart from this correction? Well, we looked at different models, GNP models, models with a given degree sequence, models with some geometric background, such as random geometric graphs, such as standard bond percolation, and also vacant set percolation. These were all simple models. We studied the existence of the question of connectivity in some of those models. We studied the giant component, the existence of a giant component of such models, and we showed that for the subcritical regime, in the case of bond percolation, we can show exponential decay using this OSSS inequality. Okay. The topic of the course in general was discrete probability models for networks, for random networks. So far, you might and you should criticize that the models that were covered so far were probably not the most realistic ones for covering real-world networks, because in real-world networks usually there is usually some geometry. But it's not true, for example, that all the edges are very close. So today we will look at the first model that is a step towards being more realistic models, namely the so-called model of long-range percolation. Okay? So long-range percolation has already a flavor that is allowing for the possibility to have longer edges, although most edges will still be short. It will be on the line still. I will hopefully in the end have some time to talk a bit about those generalizations to kernel-based models. Here we still assume that the vertex set is Z, so it's still an infinite model, but we still look at a line that is large enough if you want to have a finite model. So the vertices are just the the integers. And so on. Well, if we were doing standard bond percolation on this line, that would be boring, because unless the probability if you have an edge probability of 0.99999, you cannot have a giant component, right? So you would need to have probability 1 to hope for a giant component if you have only nearest neighbor edges. But in long-range percolation, you allow for a bit more. You say that, okay, if vertices are neighbors, such that the distance is just 1, ij is an edge independently with probability Pij in general. Let's just something, and is not an edge independently of all others with a complementary probability. But we will make this one here just 1 minus e to the minus lambda for some parameter lambda positive. So we say that if two vertices are a distance 1, then this is the probability of the edge being there, and you can see, right, that if lambda is large, then this probability is also large, right? So lambda is kind of the intensity for having a short edge. So lambda large means many short edges. You can think about 1 minus e to the minus x as x if you prefer. But then we should also have some longer edges, as I said, because otherwise this is never giving us a giant. If I minus j is at least 2, then ij is an edge independently again with a different probability, and then we have a different scaling parameter, and we have it 1 minus e to the minus beta divided by I minus j squared. Okay, again for some beta larger than 0. I apologize to the two of you that have seen this before, Michael and Clément. So what is the interpretation here? Well, it's similar. Beta is large, means that there's many long-range edges, many long edges. Okay. So if you make, just again, think about this as 1 minus e to the minus x. Think about this as x. So if beta is large, then this will also be large. So we have two parameters for this model, not alpha, lambda and beta. And you might ask whether there is a giant component or not, or whether there is an infinite component in this model for certain values of beta and lambda. So if you wonder why there is this 2 here, well, that's important. This 2 here, this square is important. If you replace if you think about this as beta over, that's roughly something like this. Right? This tells you something about the decay of long-range edges. If this 2 is replaced by something larger, then the whole proof will not work. You will not be able to show the existence of a giant component because the long edges help you too little. For exactly 2, we will show that the probability does work, so that there will be a positive probability that 0 is in an infinite component. If we had an exponent smaller than 2, well, then that would be even easier, right? So because then it means that the long edges help you even more. So 2 is right the point where it changes. So this is the result was known since the 80s, but then there was a new proof and a simpler proof that was again by Hugo Duminil-Copin, Christophe Garbon, and Vincent Tassion, which I'm following today, which is long-range percolation in 1 dimension revisited. But of course, the same object was then studied also in higher dimensions. The only difference that in higher dimensions, well, there are even for the case of no long edges, just short edges, there is already a supercritical phase, which is not trivial, right? So the ideas of using renormalization, what we will do now, they carry over with adding maybe a bit of technicalities, but they carry over to higher dimensions. I chose to present this one because I think I asked Augusto yesterday as well, and he confirmed that this is probably one of the simplest models to show how renormalization works, because you'll see there's just typically one bad box, and that makes the technicalities that usually appear in this setup relatively light. Okay, so what's the idea? Well, as we said, we want to know for alpha, no, not for alpha, for lambda and beta, we want to know what happens with the probability that the origin is connected to infinity when we have parameters for the edges with these values of lambda and beta. It's connected to infinity by a path of edges. Yeah? By a path of edges when we have lambda and beta. So there should be somewhere a path like this, something like this, right? So we start here and go maybe here and go maybe there and then go here and so on, right? So for given values of beta and lambda, we want to know whether there is a connection of 0 to infinity. Of course, this connection probability will not be 1 at the critical point, because every vertex has constant degree on average, right? This is summable here. So there is always a chance that 0 is just isolated. So 0 cannot be with probability 1. But this is a translation invariant model. So if there is positive chance that 0 is in an infinite component, well, then with probability 1 you will have an infinite component, because 0 is not special, right? It's just that we look at 0 and there's a countable set of vertices, and if for each of them there is a positive probability, then with probability 1 there will be an infinite component, and it will be unique also. Okay? And the goal to show is the following theorem by these people. which says that for every beta larger than 1, there is a positive chance that 0 connects to infinity if lambda is large enough, but finite. But it's not true if beta is, I will not show the second part, but it's not true if beta is less than 1 for So I want to focus on this part only, namely that whenever beta is larger than 1, so meaning that the long-range edges help a little bit or help enough, let's put it that way, then there exists some lambda depending on beta, such that you can make the probability that 0 is connected to infinity strictly positive. Okay. Okay. And the main result, the main idea is renormalization. Well, what does renormalization mean? Well, it means basically that you look at certain scales in your proof, making scales, in that case it will be blocks or boxes, making them larger and larger up to infinity, while maybe losing a little bit of density at each step, but making the growth of the sequence so fast and so slow at the same time, so that on the one hand, you know that your density will still remain sufficiently high, and on the other hand, sufficiently fast so that you don't have to check too often, and you will indeed end up with a connected component. So for making this a bit more concrete, we will use blocks. So the main idea will be a block at a certain level of this renormalization is a K block, namely for it's just the following. So if I take here, for example, that's my set. Let me take K equals 4. That's an example, that's not necessarily the case. And then I'm looking at every vertex making a block that goes 4 to the right and 4 to the left. So for example, if I'm looking at the block of 0, then that should contain, say, those 4 elements to the right, and that's 3, and those 4 elements to the left. Okay, so this block here is my 0, that will be the block of size k centered at 0. Well, it's not quite centered, but okay, you can see that including 0, you go 4 to the right, and then you have 4 to the left. Okay. So here, for example, if you look at bk0, and this will be -4, -3, -2, -1, 1, 0, 2, 3. And the next block they will be chosen, the next block to the right is a block that overlaps with the previous block in exactly half. So the next block will be this one then. It will contain this one and goes until here. Okay? So that will be bk1. 0, 1, 2, 3, 4, 5, 6, 7. So we think about k as a large number, and you put vertices into blocks in such a way that two consecutive blocks share exactly half of the block. Yeah? So bk, the ith block, and the I plus first block that will be k, right? And the goal of this renormalization will be that we will explore edges only within a block at one stage. And then at the next stage, we will make the block size much larger and then explore edges that were not yet explored that are further away. Then we will make the block size even larger and so on. So let's see this. Okay, first a few definitions. Okay, for a subset of the integers, a cluster in that set is a connected component with all vertices in S. Component with all vertices, whose vertices in S, whose vertices are in S, and you look only at edges that go inside edges. Only looking at edges, or all edges containing only edges with both endpoints in S. Then we say a k block, a block as defined there, bk I, say, for some I, is theta good for some value of theta, for some theta between, let's say between 3/4 and 1, if it contains a cluster of at least 2 theta k elements. And otherwise it's theta bad. Okay. So if we have a theta good cluster, well, since theta is larger than 3/4 by this assumption, it will have at least, well, it have more than actually, than 3/2 k elements. Yeah? So observe that, what does this tell us? Okay. In such a cluster, first of all, such a cluster is unique, right? So that's the first thing. Since theta is larger than 3/4, well, there's room to spare for this, but this cluster is unique. Right? Because if there's still room to spare, but that's definitely true, because one already eats up 3/2 k elements, and there's only 2 k elements in total, so that there can be only just one. But more importantly, when you have two consecutive blocks, this one, the green one, and the orange one, and they're both good, then these clusters merge. Right? For two consecutive for consecutive theta good blocks or boxes, these clusters merge. That has to be because each of them, well, this has larger than 3/2 k. So for example, if you look at the green one, it has more than 3/2 k. So imagine it contains already, the worst case, it contains already this. Then it has to contain more than half of this intersection. And similarly, the orange one, even if it contains everything here, it has to contain more than half of this intersection. And then they necessarily merge, right? That's the reason why theta is, in this argument, larger than 3/4. And the goal is to bound the probability that for a given theta and a given k, the cluster or the box is bad. Yeah? So for, let's write, because sometimes, well, not sometimes, always basically, it's not important whether we look at the box centered at the origin. So we just forget the index for now, unless we care that it's the origin. Since in the end we look at the origin being contained in a giant component, so let's say bk0 is just bk, so that we look at the box centered at 0 and set p for this k and theta to be the probability that this box centered at 0, again for some parameters beta and lambda that we fixed, is theta bad. So we want to bound from above the probability that the box is bad for a given box size. Think about k large, then it will become larger and larger, and for a certain density that will decrease. So what's the key lemma that will be this recursion or renormalization? Well, it's the following, which says that if beta is larger than 1, the final value of the sequence of theta, we will look at the sequence of theta which will be initially relatively large. So when we look at small boxes, we have a large theta, let's call it theta 1. Then we will look at larger boxes, say of constant factor larger, say that large. And we look at the theta 2, which is a bit smaller. And we look at the theta 3 and so on, which is still a bit smaller. In the end, we will do this for an infinite number of steps. We end up with so-called theta infinity, yeah, which will still be at least 3/4, so that all this observation there is still holding. And we also need, for technical reasons, that theta infinity squared beta is at least 1, such that, and this holds. Well, then there exists C0 depending on lambda and beta large enough such that we have the following statement: for every lambda theta being larger than theta infinity and every c, there's lots of constants here, but don't be scared for this. And for every c larger than this c0 and k at least 2, the probability to be bad, let me put here subindex beta lambda, when making the boxes by a factor c larger, yeah, think about c0, maybe some, say 100, for example. I make the boxes by a factor 100 larger, and I make my density of clusters a little bit smaller. So theta minus, okay, let's suppose here C0 over C. Think about C much larger than C0, so that we have here some theta prime, let's call it theta prime, which is a little bit less than theta, but we still want it in the end to be larger than 3/4 because we will iterate this. We will start with boxes with blocks of size k, and then we make the block size by a factor c larger, and we iterate, always making a little bit less density, so allowing for clusters that are a bit sparser, but still satisfying these conditions. Well, then we have this recursion, which says, well, this is at most 100th times the original probability that we were bad at the original level, meaning that the probability that we were bad at this level, okay, this was this certain number, and at the next stage, the number will be, say, already by by larger factor smaller. So let's say it will be at most 1 over 100 of this. Right? Then the next time it will be 1 over 10,000 and so on. So this will in total still be small. Plus a second term. And here we see, okay, this holds for every C, but we will pay a price if we choose C too large. So you'll see later on that it might be clever to choose C not too large. So we get a C squared or 2C squared here. The probability that we had a bad blocks squared. Okay. So that will be the main lemma to show that if we make the boxes by a large factor larger, and if we allow a little bit of less density, okay, then the probability that this is bad at that level will be much smaller than before, assuming that it was already small before, right? So this has to be small, and I cannot. So if this was not small enough, and I choose C too large, then this part will explode here. So there's an optimization to do, right? So that will be something coming from the event that you had two bad boxes at the previous layer contained in my larger box, and that's the event that we had maybe one bad box. Okay, let's prove this lemma. This is the. So that's the main issue whenever you do renormalization, to find these parameters, to tune these parameters so that you get sequences that are growing relatively fast but not too fast, so that you can do this an infinite number of times, or if you finitize it, you end up with n. You do it often enough, but not too often. Right? So this is a. That's why the statements sometimes, or not sometimes, I would say always, look a bit technical, but the idea is always the same, that you can allow for by paying the price, say, of a little bit smaller density, you can make your boxes larger and larger. Okay. Let's prove this. Okay, define C of bki, the largest cluster in the box, in the ith box, in the ith block, the largest cluster in bki remember that, what we said here, right? It's at least of size, if the box is good, then this largest cluster has at least 2 theta k elements, otherwise it's bad. And we observed that this largest cluster is unique for theta being at least 3/4. And now define the following event for I, say less or equal than C, this C there, the same C. Define the event EI be the event that the ith box is bad. So let me draw here. So we are here, somewhere is here, this is 0 here, and this goes up to this is C minus 1, say, and this is minus C here. So for I less or equal than C, okay, up to C minus 1, it should be for the positive numbers. Let EI be the event that the ith box, this is bki here, say is bad, and almost all the other boxes are good. Is theta bad? And this is theta good for almost all boxes, namely except for those that potentially overlap with the ith box. Remember that we had here, if we have here a box of size k, there is 2 that overlap. There's this one that overlaps, and this one that overlaps. So this one I will not count. For this one I don't say anything. For all j, from minus C up to C minus 1, except for maybe I minus 1, I, and I plus 1. Okay, so except for those that overlap with the ith block, these I don't consider. So if I have this EI, then what does it mean? Well, it means that I have one bad block BI. All the other blocks that are independent of this ith block, namely those that are not, they're not the ith one, not the I minus first one, and not the I plus first one, they will all be good. So we have EI basically the event that there is only one disjoint, or that there are no let's put it that way, there are no two disjoint theta bad blocks. Okay? And define then, and let Fi then the event that EI happens, and also that the larger box, this C, that's my CK box now, is theta prime bad with this new density. Okay, so that's one. One possibility how the new block, how this new big block of size ck can be bad, namely if Fi happens, right? Because in particular, observe that if Fi does not happen, namely if all boxes, or if all blocks, I'm using these words simultaneously, from minus C up to C minus 1 are all theta good, well, then in each of them we said there will be a cluster of size 2 theta k, and since they're all good, they merge by the previous observation, so we get a cluster in the whole block, in the whole big block, in the whole big box of size ck, that will also be good, right? Inside BCK, we get a cluster, since they merge, of size now 2 theta ck, and then BCK is definitely also, is actually theta good, and for sure also theta prime good, right? So that if we don't have at least one bad block on the smaller level, then it means that on the larger level, well, all of these blocks merge, not the blocks, all of these clusters in these blocks merge, and then you get a cluster which is of size at least 2 theta times the new block size. We can count the cluster size, for example, by taking every second box. Then you get these joint elements, and then you get this size, right? Because you get 2 theta k for each smaller box, and you get C by taking every second box. So in particular, or let's put it another way, so if BCK was theta prime bad, then at least one of the following has to happen. One has to happen. Namely, one, there exists an I such that Fi occurs, or there are two disjoint K blocks that are inside the larger box that are both bad. There exists at least two disjoint blocks that are bad, or at least one of the Fi has to happen, right? Because if it's not true that you find two disjoint ones, and it's not true that Fi occurs, well, then we were here, but then we would be good. So we can just take a union bound and say, so by a union bound, the probability that we are bad at the new scale Ck with the new density theta prime, well, that's at most the probability of Fi summed over all I, plus the probability that there exists two disjoint theta bad K blocks. Okay. And you can guess probably that these two terms here will correspond to these two terms here. That we will make more precise now. Okay, so there's two events here, B and A. They should correspond to these two events. Okay, the B part is easy, right? So for B, okay, so we have to choose two disjoint elements. We said that the fact that a block contains a cluster, by definition, a cluster contained only edges that had both endpoints inside the block. So whenever I'm telling you something about one cluster, it does not tell you anything about another cluster, right? So two blocks are, when they are disjoint, as we assume here, they are independent. So the probability of two disjoint, there exists two disjoint theta bad blocks, well, you have to choose just those two, right, which is basically 2C, choose 2, and they have to both be bad. Yeah, so something like this. So we have the part B, right? We just pick the clusters. And it remains to deal with the term A. And this holds for all C, but as I said, it will become useless if C is too large. So that we should be careful when setting up the C. I mean, we can choose C large, but because if this is small, then since we get a square here, the C will not hurt us too much, but not too large, right? This is clear. So that means that the next scale starting from K should be much larger, but not too quickly. What about A? Okay, since the first thing is, okay, we were actually a bit generous here, right? We say that some of these i's from C up to C, from minus C up to C minus 1 should be bad, but actually we allow a little bit less density here. So it doesn't, we do not require exactly density theta. We require only theta minus C0 over C. So there could be a few bad blocks on the side, which we don't care. And in particular with this C0 and C choice, you can check that if all Bi, Bkj, with J just in the middle around 0, well, what does in the middle mean? Well, with J in absolute value be smaller or equal than C minus C0. So you allow for C0 on the left and C0 for the right to be theta bad. That doesn't hurt us. So actually, if all of those that are in the middle are already theta good, then you can just count. Then BCK is theta prime good already. So Fi, the probability to be bad, remember that Fi was that the box is bad, and also so that the small block is bad, and also the large box is bad. So we can say, so Fi is not possible if I is larger than C minus C0 in absolute value, right? So here is my 0. And these are here the C minus C0 ones that I don't care about. Right? right? So we only have to care about these. So we fix now, so take now such an I, take I that is satisfying this C minus C0 bound. Well, Fi was defined that two things happen. That first of all, the small block is bad, and that also then the larger box is bad as well. So in particular, we had EI. Remember that Fi was EI intersection with the event that the larger box is also bad. For EI, namely for the probability that we have that the event, EI, we had the event that the ith block is bad. This was by definition pk theta. So the probability that Fi happens now, well, it's the probability of EI times the probability that BCK is theta prime bad, now knowing that EI already happens. So it remains to bound this probability here, this one here. Okay, so we know now that there is one bad cell here, one bad block. So here is my, okay, so this is, say, BKI. There are some vertices in here. We don't know anything about this one here. So this one we said that we exclude here because this one overlaps. This one we don't know what it is, whether it's good or bad. Similarly, this one we also don't know. The orange blocks we have no control over. They overlap partially with BKI. But we know that all other boxes are good by definition of Fi. There's exactly one, right? Because the event that we have two or more disjoint bad blocks is already counted. So Fi is just taking care now of the case when we have only one bad block. Yeah. Or one, that there might be, well, when I say one, okay, this one could be bad, this one could be bad, but it could not, it's not possible that this one and this one both were bad, because then we counted this already, so we can ignore this case. So there is no two disjoint bad blocks. So in particular, everything that is here is good, right? So all the blocks that are contained here these are good blocks. In particular, and here are also good blocks, right? Inside this larger CK block. So define C minus to be the union of all clusters for J smaller than I minus 2. So all these here, all these clusters here, these ones, they merge because they are all good. That's one cluster. And similarly, C plus, the same for J larger than I plus 2. These are also good, right? This is C plus here. Yeah, the union of all clusters on the right and the union of all clusters on the left. They merge by the observation we had. And they give us potentially new edges. So what's the idea? Okay, you see that these edges that are here and go here, we didn't check these edges yet, because we checked only edges that were inside a block on the previous level, but inside a block of level CK, there are still, for example, potential edges here between those here that are not checked. And the good thing is now, since these are good blocks here, there's many vertices here that belong to those clusters. There's many vertices here. There are many vertices here that also belong to this cluster here. So there are many potential edges between someone here and someone here. And since there are so many by just the density of this goodness, well, then the probability that one of them will be there and therefore will merge this part with this part, so that you get a large cluster in here, will be large. And that will be the first term. Okay? So that was the idea. So let's make it a bit more precise. So by assumption of theta goodness, C minus and C plus, the largest cluster in there, which is unique, is large enough. So for example, they both are at least theta k C minus I minus 2. And if you choose your numbers appropriately, for example, you can bound it by k half C minus I. If, for example, C minus I is larger than C0, which is, for example, 6, this is not so important. But what is important is that they are dense everywhere. Since they are good, these blocks are all good, they have many points everywhere, which means that, for example, C plus intersected with the interval, which is ki plus k, which is this point where we start, this point here. So this was ki. So let's say this is ki plus k here. This was ki here. So we go a bit further to the right. So we have ki plus k, this point here. And every intersection, every interval that I take here will contain many points of the cluster. So if I'm taking this interval of integers up to, say, 2kl, there until some point here. So here I take my ki plus k plus 2kl. Then in this red interval, I will have lots of points, namely at least 2k theta, what we expect, times L. And this holds for all L. So it's everywhere dense, because all these blocks are, you can just check by convincing yourself of the definition. So in particular, if you have these elements ordered from left to right that belong to this cluster C1, C plus, let's call them Y1, Y2, and so on, the elements of C plus, then if we choose L to be B over 2k theta, ceiling, we know that the bth element of that component cannot be too far to the right, because we are good. So in that sense, it's at most ki plus k plus 2k b over 2k theta. So if I'm ordering the elements belonging to this large cluster, starting from here, this is my y1, then the next one is y2, and the next one is y3, and so on. This is y3. So they cannot be too far to the right. In particular, the bth element of this ordering is at most at that integer. Right? So that's just counting. So this is at most ki plus 3k plus b over theta. And the same thing you can do for C minus. You order the elements now to the left. Order the elements to the left. Right, so you have here x1 up to x2 up larger than xa. You get the same argument that by the same argument you get that this is at least ki minus 3k plus a over theta. And these are these elements here, x1, x2 up to xa. That means that these edges are all relatively close. If you merge this, if you use both inequalities for yb and for xa by 1 and 2, we get that theta times yb minus xa is at most 6k plus a plus b. And you can easily check that if you want, we allowed for a little bit, I haven't erased it yet. If I allow for a little bit less density here, well, I can lose a little bit on each stage. But if this cluster of good vertices here merges with this cluster here to one big cluster, only leaving out this potential area here and maybe something to the left and to the right, then we still get a theta prime good cluster, right? So observe that if beta ck is theta prime bad, then C minus and C plus cannot have merged. That's just, again, just a bit of counting. But what's the good thing here? Well, we haven't checked anything. I haven't told you anything about those edges yet. We checked only edges inside those blocks. But this edge, the closest possible edge that we are checking is the one that goes from y1 here to x1 here. But the distance between them is definitely at least 2k, so it's definitely never in the same box, this one and this one. Right, so this edge, we haven't checked it. So In particular, all of these edges, or all of these possible vertex pairs, with one vertex here and one vertex here, they were not yet checked. So we can start a fresh exploration. But also observe no information about edges from C minus to C plus exposed yet. Okay, and therefore we can just say what's the probability that no edge from C minus to C plus. Well, we have to say that the probability that for any A and any B here, any YB and any XA, there is no edge between them. This is an exponential probability with minus beta there. I'm adding here a theta squared. And I'm dividing by theta squared. And here we have the distance. Okay. This was the definition of an edge. Remember, it was exponential minus beta over the distance squared. Here it's important that it's this squared, because by some calculations that I will not make precise now, but this is not hard, and you can check it if you want in the paper, for example. Well, claim without proof is that this sum over A, sum over B that we have there of 1 over theta squared YB minus XA squared. Well, you can compare this to an integral, for example, and then you get that this is at least log C minus absolute value of I divided by 8. Believe me this, but that's the point where this 2 comes into the game. So if this were not 2, for example 3, then this does not work, because this depends crucially on this exponent 2 here. Okay. And then we can continue to say that, so therefore the probability that there's no edge from C minus to C plus, therefore is at most A over this. That was in particular also then the probability that the block at the largest K is theta prime bad, given that there is just one bad blocks. Well, this is definitely, well, it's maybe an upper bound here. Is upper bounded by the probability that there is no edge from C minus to C plus. And then we get that the probability of this Fi, or the sum of this of these, is at most the probability that we have Ei bad times the sum. Actually, we said we have to go only from C0 minus C to C minus C0 of this number here. And then you can see that if you choose C0 large, for C0 large here, this is at most 1 over 100 times pk theta. This is theta here. And we get this term A here. Okay. So the probability that since there are so many edges that are relatively close, the probability that none of them is there is so small so that you can even take a union bound over all boxes. As I said, there was just one bad block, and this decays so fast so that this doesn't hurt for C0 large, and we get this bound, which is this term A on the. And that is the main part of this. Well, that finishes the lemma, which means that we have now a recursion on the previous, that we changed a recursion that we had on that scale to a recursion on the next scale. So if we find suitable values that this doesn't explode, then we can go on forever. And that's that allows us now to prove the theorem. We have again these technical conditions we said in the beginning. And this one. So we have to set up a sequences of these C's. That holds for all C's, but we don't want to apply it in such a case that this lemma here, this line is, the second term is useless. So let's start with C1, with theta 1 a little bit less than 1 only. C1 already much larger than C0, and then we kind of have to find a sequence of C's and thetas that means that we don't grow too fast, but that we at the same time lose a bit of density. And what you can do, or what they do, is that you choose Cn plus 1 to be n cubed Cn. This is kind of with the idea that every time you grow by a factor n cubed, well, then you get a converging sum when you get 1 over n cubed. This is kind of converging. Well, you get it here. When you choose the next density, you always get, you take the initial density and you always divide by something that is, say, 1 over n cubed, for example. Then the sum over n cubed and is still larger than 3/4, so that theta n is larger than 3/4 for all n. Remember that the lemma, this was true for all C larger than C0, so we will be able to apply it several times. And now set lambda just large enough, so large that the probability that initially in a box of size C1 and with density theta 1, well, this is so the probability that there exists 1x plus 1, that is that the box is closed inside BC1 closed, BC1 closed, is just small. So we just look at short edges in the first box. We make lambda so large so that this box is that the probability that there exists just one closed edge among the short edges, one x and x plus 1 inside the box center at the origin that is closed, is just smaller, say this is, say, at most, we choose lambda so that this is at most 1 over 1000 C1 squared. You just make your lambda large. We say we're allowed to choose lambda as a function of beta large enough. And then we make the following blocks. Okay, K1, the first block was just C1, but then we make the blocks larger. Okay, consider then blocks originally of size this C1, and the n plus first block is for each n just multiplied by this n, by this term Cn plus 1, which we defined here as n cubed of the previous one, basically. Right? So this is something like, you can think about it that K1 or Kn is something like n factorial cubed C1 to the n. And then if we set the probability to be bad at the nth level by the lemma applied, by the key lemma applied several times, we get that the probability to be bad at the next level was at most 100 times the probability to be bad at the previous level, plus 2 Cn plus 1 squared un squared. Now you can rewrite it in this way. Here you see that this choice of the Cn is not growing too fast, because Cn was only, so to say, growing by this factor n cubed. So the Cn squared here is still not growing too fast, so that will not screw you up. And then by induction, well, we have that Cn, if you just repeat and plug it in, you get that this Cn squared un is less than 1 over 1000 for each n, and therefore the probability that for each n the block of size Kn is theta n good is at least 1 minus 1 over 1000 Cn minus 2, okay, which is larger than a half. Okay, and then we can continue here, but the probability that this block, which had at least 3/4 element, has at least 1/2 probability to be good, well, then then it means that if you take the expectation of the event that we get at least 3/2 Kn in this block times the indicator that the block is 3/4 good, well, that's at least 3/4 Kn. This is at least the size of the largest component in the block, because theta n here, theta n is larger than 3/4 times this event here. It's 3/4 good, and we can just bound it by, let's say, 2Kn by translation invariance, by the probability that 0 is in a cluster of size at least 3/2 Kn. And therefore we get that probability that 0 is in a cluster of size at least 3/2 Kn is at least 3/8 for each n. Okay. So this tells us that for every n, the probability that 0 is in a cluster that is proportional to the size of the cluster is at least a constant. This holds for every n. You can do this until infinity. This is a converging sum here. So this holds for every n here. Also for, so in particular, you see that there is positive probability that the origin is in an infinite cluster. Okay. So the main idea here was to find these sequences of these C minus of these Cn's here that grows fast, so that this part here is converging. Remember that we want this to be larger than 3/4 so that we have uniqueness in the end. And this we can do because if we have here n cubed here, well then this will eventually converge. But it should not grow too fast either, because otherwise the second term that you get here will be killing you. Right? So there's a balance between growing fast and not growing too fast. And the important issue is here, so you always kind of explore fresh edges. So you look at one scale and the next scale. Maybe you lose a bit in one parameter, but you gain a bit in the other parameter. So here you make your boxes larger and larger. You're allowed to lose a little bit, not too much, because otherwise this uniqueness claim will break down at some point. But you can do it until infinity. And this is this idea of renormalization. As I said, this has worked very, very well for most of those geometric random graph models. That being maybe the least technical one. Still, it's technical. What's bad here is that, so if you want to do it the very first time, well, the idea is not too difficult, but you will probably not get all the constants exactly in the right area. You will have to play around a bit until you balance these effects. Okay. So in the remaining 0 minutes. In the very beginning of the lecture, of the very first lecture, I mentioned that I will talk about kernel-based random graphs, which would have been the only time where I would have talked about my own research, which I will not do, of course, now. But the good thing is I was not completely lying when I was saying I will talk about this in IMPA, because I was giving a talk in the seminar in June here in IMPA online, and you can look at this, and it was also recorded. So if you look at session 136 in YouTube I googled it, of the IMPA probability seminar, then you'll see that you can see how to apply this also to graphs where you have a Poisson point process in d-dimension instead of just having one single line. D-dimension in general, and moreover, on top of that, not just the probability of having long edges, but also vertices that have a certain weight. So it's not just that each edge between two vertices depends on the distance, but it will also depend on the weights of these two vertices. And we assume some power laws on these weights, and then the probability of an edge depends both on a kernel function of these weights, say the product of these weights, for example, and also on the distance of these weights. And then you finally have, maybe, hopefully, a model that is more realistic for random networks, But the tools are similar to the tools I presented in all these lectures. So it's more technical, but I guess from a conceptual point of view, it's similar. Okay, that's it, and I hope you enjoyed the course.